Hello everyone, welcome to MLAS 700, Advanced Cybernetic Systems Development, Learning Activity 12. And what we're going to be doing this week is a little bit of a hybrid. We'll be doing our lecture, and it'll be a two-part. We'll be diving into the machine learning models. Not all of them, there's just way too many to do that with, but we're going to start doing a deeper dive into supervised learning. We'll pick a model, and then we're going to dive deep into that model, even kind of going through the math. And we'll do that for supervised learning, and then we're going to have a part 2 next week where we're going to jump into unsupervised learning and do the same thing. We'll give a treatment to unsupervised learning models, and we'll find a machine learning model that we will dive into in more detail. Then for this week, to help demo this better, it's easier for me to show these with Python. So our lab's going to be mixed between Python this week for demonstration purposes of a machine learning model, because it is so much easier to do it that way. There's visualization tools, there's extra tools that we can use to help us do model evaluation that don't exist in the Arduino IDE world. So we'll use Google Colab for our IDE, and then for our lab, that we're going to be one of our labs rather this week to help explain linear regression. We'll be using Python and Google Colab, and then we'll circle back with the second lab this week is going to be back on our kit. So so the reason why I'm doing this is because I want to be able to show you linear regression. We are working our way towards a linear regression model, and it's the entry point into everything supervised learning, whether it's a neural network, whether it's multivariate regression, whether it's logistic regression, whether it's a k-means, whether it's any type of movement into supervised learning. Usually starts off with a linear regression model, and typically it's a simple linear regression, one independent variable, one dependent variable. That's typically how that works. So we're going to go ahead and start off with our introduction to, whoops, come on, over here. We're going to go ahead and we go into the different machine learning types. As a recap, we've done supervised, unsupervised, semi-supervised, and reinforcement learning. And we did that with the fruit exercise earlier in a lecture from earlier in the semester. We also did that with a series of string text, right? BOX. We created a series of strings, or a series of letters within a string, and then we did an explanation of differences between supervised and unsupervised, and how that kind of plays out, as well as reinforcement on that string, right? And how you predict and reinforce or influence the movement of what can happen next within that string. Okay, so if you want to get a review, go ahead and go back there and learn through that. Go through that and then relearn, just kind of get re-caught up on those concepts in our earlier lectures from week 1. And then you can come back here if you need a refresher. That's week 1's good for that. But for us, we're going to start off with supervised learning. We're going to dive into supervised learning here. And we're going to use this overview of what supervised learning is to start with, and the different types of use cases. And then we'll head on over to evaluation metrics. And then from evaluation metrics, we'll kick us off into linear regression details. And so let's get us started with this right here. So learning from a labeled data to predict or classify. So that's supervised learning. Supervised learning is all about, just as it sounds, it uses pre-labeled data, usually from a human, not always, but nowadays not so much. You've got machines that are pre-labeling data for us now, because we've gotten that good at it. But in the early days, it usually was pre-labeled data. So, for example, if I have an image library of apples, oranges, and and bananas, right, and I wanted to point a camera at orange, banana, or something like that, a conveyance system, right? So that I could separate out, here's a banana, here's an apple, here's an orange, and it's let's say all these fruit are coming through on a conveyance system, and I have a camera with a robotic hand attached to it. Well, then I can use that camera to do what's called a sorting task. Well, to do that, you need a machine learning model, and typically you would use pre-labeled data. And then I would go through and then label and say, whenever you see this, that's a banana. Whenever you see this image, that's an orange, and so on and so forth. And then you would create enough of these sample sets that you could load that up into a neural network, train the neural network to then be able to distinguish that, and you would pass that off to a program to say, hey, at this point, once you've figured that out, now the robot can then go and pick out, based on the pre-labeled training data that it was provided, what is a banana, what is an orange, and what's an apple. So that's supervised learning. So so think of it as training data versus no training data. Unsupervised data doesn't have training data, whereas supervised data has training data. Supervised data is used for classification and regression. So classification is different from clustering. So you'll hear this come up a lot. People mix this stuff up regularly, and so clustering is an unsupervised task. That's an unsupervised learning mechanism when I'm doing clustering. Classification is a similar activity, but it's using supervised data, and it's pre-trained, pre-learned, pre-labeled. So in other words, what I mean is, let's go back to the fruit exercise. That's a classification exercise. When I go through the process of training a model up, I'm using pre-labeled data that a human set up in an image library, and then I train a neural network on that image library, and that's so that it can classify what it's seeing. And there is a prediction element to that. I am predicting what I am seeing, right? I am predicting what I am classifying. What are the odds that what I am seeing is an orange? That's a prediction. What are the odds that I'm seeing a banana? That's a prediction. What are the odds that I'm seeing an apple? Those are all prediction questions, but they're what's called predictive classification. Then there's ones that aren't predictive classifications, where I'm doing a regression, which is a prediction. In this case, an example is like on housing prices. I want to predict what the future of a particular temperature is, or what the future prediction of the housing market's going to be, or what the future is going to hold. It's a forecast of what's going to happen next. That's different from classification, or a predictive classifier. So a regression in this case, for just a regression for regression's sake, is about what's going to happen next. Typically, it's either an estimator or an estimation, a forecast, or a prediction. And those would all kind of fall into regression world. Okay. So there are many common algorithms in this space: linear, logistic. Logistic has to do with 0 or 1, a yes or a no. It's a binary regression. Uses a sigmoid function. Decision trees, that's another one. Random forest is a form of decision trees. It's an ensemble method. There's support vector machines, k-nearest neighbors, neural networks. Those are all common supervised learning. And on the other side of it, you have unsupervised, and unsupervised is going to be principal component analysis. It's going to be t-SNE. It's going to be k-means. It's going to be DB scan. There's a lot of different unsupervised learning models as well, and they operate off of, again, not having training data, and those are clustering algorithms. And so typically, again, whether you're doing supervised or unsupervised, whether it's k-means or whether it's k-nearest neighbors, KNN, as an example, not the same, but doesn't matter. Typically, whether it's supervised or unsupervised, we almost always start off with linear regression as our entry point. I reemphasize that because we're just about getting into where we're gonna dive into that today. So there are a lot. One more thing I want to say about this is you'll see the bottom one here, this neural network. So artificial neural networks. This right here is a means for us to jump off into deep learning. When we talk about convolutional neural nets, or when we talk about recurrent neural nets, or when we talk about deconvolutional neural nets or generative adversarial networks, those are all going to be neural networks and a class called deep learning. And so that's a part of supervised learning, and that's also what forms the basis of large language models, or large multimodal models, LMMs and LLMs, so that would be your open AIs, your chat GPTs. That is the embodiment of, really, it's kind of that's where you're going to see those kind of architectures, is on the neural networks in the deep learning world, and most of the architectures that you're going to see are built off of, fundamentally, from neural networks. Okay, so moving on over to evaluation metrics. So we're going to take on, we're not going to do all of these, but we're going to take on two. So typically when we're doing supervised learning tasks, there are a lot of metrics that we use to make sure that our model is performing accurately, and that it is grounded in reality. When we pointed at data that captures a natural phenomenon, and then we train a model on that natural phenomenon, can we expect to get reasonable results on the output and the prediction of that output, right? We can use a lot of different metrics. There's only going to be two that we're going to go through today, and that will translate over into what we do in our lab as well, in our linear regression lab that we're going to be doing in Python. So you've got accuracy, precision, recall. You've got an F1 score. For regression metrics, there's mean absolute error, the MAE. There's the mean squared error, MSE, and then there's the R2. Which is sometimes, you'll see that sometimes, the coefficient of determination. If you've taken statistics before, all this is going to be, you'll start to kind of, some of it will be coming into you more readily, but that's okay. If you've never taken statistics, that's all right. You don't have to know that. You don't have to have a stats background to come in to take this course, but it will help you. Some of this will look familiar to you as we move through this, but these are some. I'm going to teach you how to read these and what they mean versus the statistical underpinnings of them. Right? This isn't a stats course. This isn't a math course. This is a programming course. So that's what we're going to focus on. And then, oh, by the way, we're going to teach you a little bit about probabilistic programming. And so those are kind of some of the things that, as you move along, you'll get a feel for, right? You don't have to be a mathematician to do this, although you do have to be you have to have the intuition to understand what it is that's happening underlying it, but you don't have to run through and be able to do all the math. That's again, not what we're trying to do here. Okay, so let's talk through, now that I said it's not about the math, let's just high level talk about it, though. And again, this isn't going to be on a test, but let's just run through high level what we're talking about. So Starting off with linear regression. All right. So a linear regression is about modeling the relationship between one or more independent variables, and we call these predictors, and a dependent variable target. And so in what we're going to be doing in our demo in our lab is going to be a one-to-one. It's going to be a one IV independent variable predictor against one DV dependent variable target. And so typically in a simple linear regression, not typically, but in a simple linear regression, you use a straight line to describe the relationship. And that's usually what this is expressed at right here. And if you remember your linear algebra, y equals to mx plus b, that's what this is. That's essentially what this equation is. Y equals to mx plus b. And in this case, we're just using different slightly different terminology. So this y right here, that's the dependent variable, and that's the outcome that we're trying to predict. This right here is the outcome that we're trying to predict. X here is the independent variable, and that's the input that helps make the predictions about y. In other words, this helps to make the predictions about what's going on right here. So this is the output, right? And then our beta sub 0 here is the intercept. And that one is where the line crosses the y-axis. And we've got an explanation here visually kind of depicting what's going on. And then our beta sub 1 is the slope, which shows how much the y changes from a given x. Y changes for a given in x. So that's right. It's your rise. Remember that back in linear algebra, that rise over run type of thing. Well, that's what's going on here. And then this E symbol here, that is the error term, and that accounts for the difference between the predicted variable and the actual values of y. Usually due to the factors not captured by the model. That's probably the best way to explain that. And so let me see if I can remember how to relay that back again to you. So that's accounting for the differences between the predicted and the actual values of y due to factors not captured by the model. So that's what the error term represents. Okay, let's see. All right. And for people that are interested in the more details on that, the epsilon, this error term, the E here, that's called epsilon. It's another piece that is something to kind of take into account is random fluctuations in the data, and then model inaccuracies. So there's really three big things that pop up with the error term: unobserved factors, random fluctuations, and model inaccuracies are the other couple things. So outside of that, I don't want to spend too much more time on this because I want to get down to the next part of our discussion, which is focused on our loss function, our mean squared error. So let's jump down to the loss function here. So the loss function, when we're talking about the loss function, this is a pretty important piece of it because we do use this in an evaluation. And so the goal of the linear regression is to find what we'd call a line of best fit for the data. And sometimes when we've got multiple, so we're going to be doing a simple regression, but when it's a multiple linear regression, there's usually a hyperplane that's involved. But for us, it's just a line of best fit for a simple linear regression. So And typically the loss function, it's going to measure how well the model predicts the actual data. And so usually a common loss function used in linear regression, and so this is what this is a mean squared error in MSE, which calculates the average. It calculates the squared difference between the predicted and actual values. That's what this is. That's what this equation is doing here, or illustrating that. So y sub I, this one here, and we're doing a summation of y sub I minus y hat sub I squared, and the summation of that. But y sub I is the actual values of the dependent variable. So this right here is the actual values of the variables themselves summated over themselves, right? And then y hat sub I is the predicted value. That's the predicted values from the model itself. And then n is the sample size, right? That's the number of, well, it says it right here, the number of data points, but that's the sample size. And so that's the number of times that in other words, that's the number of data points, the number of samples that I'm putting through the summation, where I'm taking that y sub I minus y hat sub I squared, and then summating them, of course, across all the data points. And then I'm going to get what's called an MSE value out of this calculation. And so this is going to give me what's called, or I should say, sorry, this is going to be a scale dependent. Let me move over to my notes here, right? This scale dependency. So that when I say that, you have to, the MSE value that you're going to get by itself isn't useful unless it's compared against what is the measure of it within the scale that it was calculated against. And so a lower MSE is a better predictor. It means that the model's predictions are more closely approximating what the actual real-world values of we're seeing occur. And that's important. And the higher the MSE as it relates to the scale that it was calculated against, if it's a higher MSE and it's at the top end of that scale, then that means that we've got a problem with our model and it's probably not useful. In other words, it's not a good predictor. There could be a number of reasons for that. And some of this, I'm throwing a lot of terms at you. Some of this just takes practice. This is not easy stuff to grasp. Trust me when I tell you, this is stuff that you just have to play with it. You have to get comfortable with it. You have to go play with data, expand on data, use these algorithms against the data, and then slowly work your way into it. You're going to come across new terms, you're going to come across new ideas, you're going to come across new ways of doing things, and it's a really, really big space. And so when it comes to this, it does seem challenging, it does seem daunting, but trust me, the more you get into it, the more it's not terrible. Stuff starts to kind of click. On your first couple of go-arounds, you start to get a feel for like, oh, that's what that means, and that's how I can use this, and that's what this explainable variance means over here, and that's what an R-square means when it's a coefficient of determination, and oh, by the way, those are the two same things, right? We're using the same terminology, and you're going to see a lot of that. Just it's okay. Just take a deep breath. We'll get through it, and it's just practice. Yeah, it's just getting practice with it. So this is going to have more context as we get into the demo. It's plain and open hand of cards. When we get to the demo, it'll make a lot more sense. Okay. All right. So that's the MSE, and then another one is this. This isn't an evaluation metrics. This is a way for us to influence an evaluation metrics, but through what's called ordinary least squares, and OLS is a way to minimize loss. And so the goal of OLS is to minimize, typically in this case, to reduce or make that MSE value as low as possible. So the idea is OLS is trying to minimize the error between the actual and predicted values by adjusting the model's coefficients. And then, and another way to say this is, we're looking to find the values of beta sub 0 and beta sub 1. These two, we're looking to for the regression, we're trying to find the values of beta sub 0 and beta sub 1, or the entire set of coefficients in a multiple regression, in a way that minimizes the total error. Yeah, so that's we're trying to minimize the MSE, or this mean squared error, and we're trying, and that's what OLS does. It's an optimization that takes the partial derivatives of the MSE, with respect to the coefficients, and then it sets them to equal to 0, and then the process, the idea is that what this helps to do is optimize to give us the best fitting line for, if it's a multiple regression, a hyperplane, but in this case, it's just a best fitting line, because we're just doing a simple regression. It's just a line of best fit. And so, yeah, that's, again, this is, I'm not trying to turn you into mathematicians. I just want to walk through what the math is doing and what we're trying to get to. What even something as simple as a linear regression gets pretty complicated, from the math perspective. But from a programmatic perspective, it's really straightforward. So this will be fun. It'll be fun on the demo. Okay, so I think, let's see, is there anything else I want to do here to explain? No, I think we're good here, and then I'm going to get moving over onto our prediction. Okay, so after we've done all that, we've gone through our first few steps, our first 3 steps, and we're now ready for prediction. Once we have the model trained, because this is a supervised model, and we've found the line of best fit, then we can use a prediction. So we can then take that and then create an equation to make predictions for unseen data, and that's really what we're trying to do. And so, in the case of the easiest way to say that is, if for example, if we create a prediction, and usually it starts with a very simple hypothesis. Before I go over to R squared here for a second, let me say this. So if I want to create a prediction, it usually starts with a good hypothesis. It's an if this isn't going to occur, if this XYZ thing is going to happen, then I'm going to observe the effect of what it is that I'm going to do. So if, for example, if I give a plant a little bit of water, it grows by this much amount. If I give it this much water, it grows by this much more amount. And so that is a prediction. So what I can do is I can create a whole bunch of plants. I can control, keep all things equal, like sunlight and everything else, and soil and all that. And then I can say, okay, I'm going to control all these others, and I'm going to standardize those. But then what I'm going to do is I'm going to variate how much water I give my plants. And I'm going to standardize this by saying, all plants are equal. They're the same plants, same breed of plants. And then what I'm going to do is I'm going to then give different plants different levels of water. So then I can measure its growth. Well, then what ends up happening is I'm creating a training data set that I can feed to a machine learning algorithm then to say, in the absence of actually doing the experiment, because the experiment was done before, I can now predict what the future of that looks like on a regression line. So in other words, I can now say, okay, well, I don't need, because I've had the pre-training done for me, I've created a supervised learning model based on the observed outcome of an experiment, and then I can predict, oh, well, this is what might happen if I give it, instead of 3 drops of water, 4 drops of water, let's say I gave it 6 drops of water. Well, great, then I can predict what is going to happen next in the absence of information. So that's what we mean by that when we say that we can use an equation to make predictions on unseen data. Now moving on to R squared. This R squared here, this is like one of your go-tos. You can't use it in isolation by itself. Typically, a model evaluation, just as an example, like I did for my dissertation, I did structural equation modeling, and my model and that just was one. I had a PCA, I had an EFA, I had a CFA, and then I had an SEM. So I had I had 4 different machine learning models, and each one was used in a different context to evaluate my data, and each one had different evaluation metrics. So principal component analysis was my entry point, and then that was just to give me some explainable variance along with to help me understand, am I going down the right path? And then when I had multiple metrics that I had to compare against each other, then I would take CFA, exploratory factor analysis, then move that over to confirmatory factor analysis, and then move into a full structural equation model. And each one of those has its own evaluation metrics. As an example, structural equation modeling. For me, there's probably a good 15 different evaluation metrics. I'm going to only take you through 2 for linear regression. But I had to do 5 for mine. For my dissertation. That's just to kind of give you an example of how complicated it can get sometimes for this stuff. But R square is a very, it's one of your first go-tos, and you do want to take a look at that. MSE is going to be a good one, excuse me, as well as R square. So after we've trained our model and we've got a good fit, and what we usually do is typically we'd use this R square to measure the proportion of the variance in the dependent variable that is explained in the independent variable. And so typically what we'll do is this R square, what we're looking for is it to be as close to 1 as possible. If what we're looking for is explainable variance. So and sometimes we'll call this the coefficient of determination. You'll see that sometimes in the output, and then sometimes you'll see it put as R dash squared. Sometimes it's R2. Sometimes it's R super 2, or something like that. So there's just all kinds of different languages that you'll come across. But again, this comes with practice. So when you see coefficient of determination and what you're looking for in this R2 value, you're looking for it to be as close to 1 as possible. It doesn't have to be 1, but anything that, and a lot of times you don't want it to be 1. It's kind of a running, it's not a joke, it's just something that we kind of laugh at. But if you see something that is like anything that gets close to or is like on 1 or 0.99, 0.98, we kind of almost don't like that because it's too perfect. We don't want it to be too perfect. We want good, but we don't want perfect, because as soon as if we see R equal 1, that means that I would question the data. If it's an R equals even 0.99, I would question the data. That would be something that I would be a little leery of. Of course, same thing on the other side. If I saw something on, that was 0.0, that's a problem. It's not usable. But again, on the other side of it, those are some things that just from experience you kind of pick up. So, okay. So you're asking, well, what is a good value for R squared? Well, that's something that is also model dependent. You can have an evaluation of 0.5, and it's just that's okay. You can even have it be a little bit below that. That's still okay. As soon as you get under 0.3, and it's context specific too, what kind of data you're looking at, then it starts to get into unusable territory. This is what's called the standardized metric. R2s are usually standardized, whereas MSCs are not standardized. And what I mean by that is R2 is not scale dependent. So whereas MSCs are scale dependent. Typically, back here, MSCs are scale dependent. And what that means is that this being scale dependent for the MSC means that you have to take scale into account when interpreting the MSC. Whereas here, you don't. The scale is baked in. It's from 0 to 1. And that's the scale that we're working on. In other words, it's standardized. So R2 is a standardized evaluation metric. Okay. Woo, man. But that's why I wanted to pick these two, MSC and R2, because it's a good entry point in doing a linear regression to help you understand in the demo what we're looking at and get you kind of on the right path. So, all right. So here's, and also to reinforce, we're going to end the semester on incorporating a machine learning model within our Arduino. So we're working our way towards that, and so this is just one way of us doing that. That's why I'm spending quite a bit of time on this one, because we are going to be using a linear regression. Okay. All right. So here's a recap. So linear model, it represents the relationships between inputs and outputs. A loss function quantifies the error between predicted and actual. And then an OLS is an optimizer that finds the best line of best fit by minimizing the error, and minimizing the error being the MSE. And then we have a prediction that occurs, and then that's step number 4. And then that uses the pre-trained model to make predictions. And then finally we do a model evaluation. So this is very cybernetic-y at this point, because this requires, and this is a second order cybernetics problem. So because this is a model evaluation that requires a human, i.e. you as the researcher, to evaluate it, which is you as the human in the loop. So you're a human in the loop, which is a second order cybernetic problem. And so that's just to kind of put a cybernetic spin on what it is that we're looking at here. And then the model evaluation, we're going to be using 2 metrics. We're going to be using the MSE, and then we're going to be using the R2. Okay, let's see. What do I have left here? All right. So that puts a summary, a recap of us for linear regression. And so let's just kind of now come back up out of linear regression and then compare supervised with unsupervised. So now that we've spent some time in the supervised world and diving deep into a single algorithm of a supervised learning model, let's pull up and then just do a quick comparison of supervised versus unsupervised. So here's a recap of that. So the data requirement for supervised is labeled data. Unsupervised is unlabeled data. So there's no pre-training that goes into it in unsupervised, and there is training data that goes into it for supervised. Another piece of that is the output for a supervised model is prediction, and whereas unsupervised we're doing clustering, right? We are doing grouping and feature. They call it feature transformation, and that's fine too. But what we're doing is we're doing clustering, and then use cases for supervised. You can see here image recognition. I mentioned that before. That's a good one. And then unsupervised is you can do customer segmentation. We used to do that a lot on the industry side. Spent a lot of time doing some fancy customer segmentation for market sales analysis. But also all kinds of other stuff. Supervised you can do. Unsupervised is such a powerful tool, and especially considering that you're talking about some of the algorithms that have been around for so long, hundreds of years. So okay, then really what it comes down to is a lot of times people will say machine learning as a catch-all phrase, or artificial intelligence, and they don't really know, supervised versus unsupervised. You don't start with supervised and unsupervised and then work your way towards the business cases. You actually work your way from the business cases back. So in other words, if someone comes and says, hey, I've got this image recognition exercise, then what you can do is then say, oh, okay, well, if it's image recognition, then here the machine learning. That's a supervised, it's a supervised problem. I should say it's a supervised solution for an architecture to image recognition, and therefore I'm going to use those machine learning models on the supervised machine learning side. You don't want to go at it reverse. In other words, you don't want to say, hey, I'm comfortable using T, stochastic nearest embedding. Okay, great. So if you're using TSNE as an algorithm, and you say, oh, I'm going to use that, and then go find your business case, you're going to find yourself in trouble, because you don't work the algorithm through to the business case. You work the business case back through the multiple algorithms that you might be using. That's how you get into successful development of a use case using machine learning. That's just my experience. There's really no other, in my opinion, there's no other way to go about it when you're looking to get these machine learning models used in an industrial context. So, okay. So hands-on. So our lab this week is going to be focused on Google Colab, using Google Colab and Python as a programming language. We'll be going through a demonstration of a supervised learning model, in this case a linear regression model. We're going to do a build, and then we're going to do a build off of some pre-trained data. We're going to train the data, and then we're going to create an evaluation, and then we're going to evaluate the metrics and how well our model is going to do. We're going to also, I'm going to throw a little bit of something else in there. We're going to use Gemini to help us with some of this, because this is kind of fun. I like using the LLM to help explain things for us. And then the two things we're going to be using Google Colab, but we'll be using scikit-learn as well within that environment. Okay, so that's all I've got for our lecture this week. Head on over to the next lab, or the next learning activity, which is going to be a lab, and then we'll jump over into Google Colab and run through this supervised learning demo. Again, this provides the basis. This is the fundamental basis for what's going to happen in our Arduino exercise when we go to build this out, a linear model, and load that up into our Arduino architecture, and then do a prediction. So yeah, this will be fun. Okay, that's all I've got here, and I will see you over in the lab.